Hello and welcome. Let's look at lesson 9.7 today, and we are working with the Lagrange error bound. And let me see if I can hit pause. I don't think so. I forgot to get my pen set up before we started. So just let me take a moment here, get these so they're thinner. I'm at home recording, so it doesn't act quite the same. It doesn't remember settings when you're not on the school server. All right, well, that gives me a few narrower fonts here. All right, we are on Lagrange error. And like before, we had that alternating series error that was the next missed term of the alternating series that we could determine how much we were missing. Um, And kind of the same thing here today. We're going to define our Taylor polynomial approximation to whatever nth degree we want, and then try to define how much error or remainder we have that we're missing in our approximation. So the big idea that we're seeing is the blue curve is our cosine curve. And if I created a um, fourth degree Taylor for cosine and plotted it out, you'd see the red curve. Well, within a certain region, it's hardly, indistinguishable between the red and the blue curve. But as I move away from my center point, you do start introducing some error. And then over on the right, you're seeing e to the x. The red curve is the fourth degree Taylor. And the same thing, there's for quite a ways, we have identical looking curves. So, but we do know there's some error with using a Taylor approximation. And here, e to the x is in red. The dashed one is a fourth degree Taylor's for e to the x centered at 0. And if I zoom in, we can see, yes, there is some difference between the approximation and the actual curve. So how do we define things? Well, like before, we know that our function can be described by the Taylor approximation or the polynomial approximation to an nth degree, whether that be fourth degree, fifth degree, so on. And then there would be some missing amount, which we'll call the remainder of that nth degree. So if I added my approximation, my Taylor polynomial, with the remainder, that would give me the exact value. Our error, which is our remainder of nth degree, could be found by simply subtracting, couldn't it, the remainder from the actual function. So, oh, I'm sorry, I should say the p. If I want to solve for r, subtract p sub n of x from the original function. And that would be the difference giving us remainder. But most of the time, we're doing a Taylor approximation because we can't actually, come up with the actual value of the function by hand. Now, with a calculator, of course, we could do a lot more. So we're really going to focus in on how to define or bound this error. And the Lagrange error is a takeoff of a Taylor's theorem remainder. And this one's saying the exact value, r sub n, of x. X would be wherever I'm trying to estimate. So maybe I'm doing a cosine of 0.3, which is what we're going to do in a little bit. Then my x value would be that 0.3. And what is the remainder as I calculate out at 0.3? So it's saying look at the n plus 1 derivative evaluated at some z value. Okay, this is where this one gets a little tricky. Over an n plus 1 factorial at x minus c, our centering point, to the n plus 1 degree. So the nth degree remainder is going to be equal to an n plus 1, kind of that next calculation in the approximation. But getting this f of the n plus 1 derivative evaluated at z is where it's tricky. And z will fall between my centering point and the value I'm interested in. So if I had cosine of 0.3 and I'm centered at 0, then my z would be some value between 0 and 0.3. The quest, as you can see here, is to find z that makes the perfect remainder. However, if we could get that perfect, then we probably wouldn't need the Taylor polynomial. So Taylor's theorem is almost like an impossibility of, fine-tuning that z value to come up with the actual remainder. So that's where Lagrange steps in, and he looks at it and says, instead of trying to find that precise location and evaluate the derivative at that z value, let's just talk about what is the max value of that n plus 1 derivative at some value z. And we'll maximize that. So this becomes an easier task. All we need to is estimate the max value, and you're going to see how much easier this is. Doesn't seem like it right now, but trust me, it'll be okay. So we're also noticing we're putting absolute values on this, saying the remainder is less than or equal to, and we've got these absolute values going on so that we can do take our Taylor's approximation at n evaluated at x and add and subtract this remainder from it and come up with what the actual is, or bounds for the actual. All right, let's move forward. So these steps are still in place. We'll evaluate our approximation, our Taylor approximation, at whatever degree we were told to do. So that'll be actually putting numbers in and getting out the numeric value for that Taylor's polynomial. Then we'll talk about finding the max value, the n plus 1 derivative, and doing that. Finally, we can add and subtract that max value of the remainder from our original approximation and get the bounds, the lower and the upper bound. So let's just hop to it. Example 1, our function is cosine, and we want to evaluate the cosine at 0.3. So we're going to use a fourth degree Maclaurin polynomial to approximate the cosine of 0.3. Well, let's write out, I need to flip my tablet. Let's write out our Taylors. So we know that a Taylor's for cosine. Let's see, cosine is even, so it starts off with a 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial. And we just wanted a fourth degree Maclaurin, so we'll stop there, won't we? It'll just be those first 4. Now, I want to evaluate this when x is 0.3, and I know that my centering point is at 0 because I did a Maclaurin. So I'm going to pop in 1 minus 0.3 squared divided by 2 factorial, or just 2, plus 0.3 to the fourth degree over 4 factorial, and come up with that value. And that you would just put in your calculator and do. So 0.955338 is what my calculator said. And this is our P sub 4 of 0.3, our Taylor approximation for that cosine. All right, so we've got our approximation. Now, how far off is it? So we're going to find the max possible value of the remainder by using the n plus 1 derivative, right? So kind of that next term in this sequence, right, that we would have been missing. So we're going to do that by looking at the fourth, let's put absolute values on this. The fourth degree remainder of 0.3 will be less than or equal to the max value of the fifth derivative evaluated at some value z, and then I'd have x minus c, but our x is 0.3 minus our zeroing point, our centering point, which is 0, fifth degree 5 factorial. Now, when I think about the derivatives, if I'm starting with cosine, the next derivative would be negative sine. The next derivative would be cosine, negative cosine. The next derivative would be sine again, wouldn't it? What is the max value of the sine function or even cosine function in this case? Because we're on the fifth derivative, so looks like we'd probably be at what, cosine? The max value of those, they are always less than or equal to 1. So we can use 1 to replace right there for that max derivative. All right? So we're going to have that my remainder, then evaluate to get the max possible value of the remainder. Yeah. So our fourth degree remainder of x will be less than or equal to, our max value is 1 over a 4 plus 1 factorial, getting us to 5, and then x minus c to the 4 plus 1, which is equal to a 1 x to the 5th over 5 factorial. And now if I evaluate this at 0.3, the absolute value of this will be less than 1 times 0.3 raised to the 5th over over 5 factorial. Lost track where it was. That would be absolute valued as well. And that, if I put that into my calculator, I ended up with 0.0000402. And this is my max error. Now, finally, to get the last of it, we're going to take our Taylor approximation, degree 4, which was this number. So I'm going to say f, the actual function value, will lie between 0.9, I have 55338 minus my max error of 0.12342, and then 0.955338 added with that error calculated at 2 10,000ths, is it? And that's going to give me a range between 0.955318 is less than or equal to the cosine of 0.3, less than or equal to, those should be less than or equal to's, 0.9555358. I know it'll fall between those values. And that was only taking the first 3 terms of our approximation. We had a fourth degree approximation, isn't it? And look how close we've got that down. It's amazing. So the trickiest part is coming up with what your max is. But this is a rough, this is a very much an estimated value. So you really kind of want to overestimate, if anything, so that you get your bounds, your lower and upper bounds, to be accurate. Find the fourth degree polynomial. So first thing we're going to do, we want to estimate e to the 0.6. Well, first off, e to the x is the series at 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial. That gets us our fourth degree polynomial. If I evaluate e to the sixth of this, I'd have 1 plus 0.6 plus 0.6 squared over 2 factorial plus 0.6 cubed over 3 factorial plus 0.6 to the fourth over 4 factorial. And that, if you use your calculator, gets you a number in this range, 1.8214. All right, so if we were centered at 0, here's our centering, right? Our C value is 0, and this looks like it's 1. We're coming in, right in this area is what we were estimating at. We're finding e to the 0.6, and it looks like this should be really, really close in that region, doesn't it? All right, so if I look at the derivatives for e to the x, it never changes, does it? It's e to the x, it's e to the x, and so on. So when I come into looking for the remainder of fourth degree, it will be less than or equal to the max value of the fifth fifth derivative evaluated at some z, and this we want an absolute value, over a 5 factorial, and then we'd have our 0.6 minus 0 to the fifth power. Now, what do you want to estimate the fifth derivative to be? I would think, okay, e to the 0 or e to the first, somewhere in this range is our value. Remember, this z value should lie between 0 and 0.6, but I'm not going to be able to evaluate e at 0.6, so I'm just going to step that up and evaluate it at 1. And I know e at 1 is about 2.718. That's kind of cruddy to put in there. So this is the liberty that we have. We can just call it 3. I'm going to round it to 3. It definitely is larger than what it needs to be, but that means that my remainder will be made, a little bit larger. So I will have my upper and lower bounds when I'm finished, for sure containing the actual value. So, and this would be 0.6 to the fifth over 5 factorial. Using a calculator, this will be less than or equal to, too much stuff in the way here, my fourth degree remainder for 0.6, I could put that in there, of 0.6 will be less than or equal to 0.001944. Okay, if I want to find the lower and upper bounds, then I'm going to say that f, these should have equal signs, f of 0.6 will be smaller than or equal to, and now I'm going to go back and grab that approximation of, oops, it jumped on me, 1.8214, our fourth degree polynomial approximation, added on with our 0.001944. 0.01944. And then on the other side, take our Taylor approximation and subtract 0.01944. And that'll give me my lower and upper bounds. Very good. You have this homework here, and same idea. They are, so this one, let's just read number one. F of 0.8 is approximated by a third degree polynomial. And there's our third degree polynomial. Given that the fourth derivative of x is always less than or equal to 1.4, they are providing to you the max value of the fourth derivative. So they're telling us what to use when we go into our fourth degree remainder. Remember, this would have been, this is a third degree polynomial, isn't it? Third degree remainder, fourth derivative then of z. And we want to maximize that. And then it would be x minus 0. X minus c. So my x is 0.8. My c value, I can tell c is equal to 0. So it's going to be that raised to the fourth power over 4 factorial. And then just go ahead and calculate that out. I'm looking for one. What's the max error? I think all of those will be fine. With an error less than, that's the one I wanted. You are just going to have to try different degrees to see where you finally end up with a remainder that's less than 0.001. And in this one, I can see they're structuring. The derivative is always less than 1. So I'm going to set a max value equal to 1 for that derivative notation. So I'd have 1 times x minus c to the nth degree over n factorial. And this is going to be, let's call this n plus 1 for the r sub n remainder. And it looks like your x is going to be at 2 and our center is at, or 2.5, centering at 2.0. So c value is 2, x value is 2.5. And you're just going to sit there and play around. Maybe start in the middle, throw a 5 in there, so that I'm looking for the fifth degree remainder, which would put 6's in our place when we do n plus 1, and see if it's less than 0.001. If it is, then maybe I can move down to a fourth degree and see if I can still stay under that. So it is a little bit of a guess and check game on number 5. Okay? That's all I have for you.